Okay, so let's go for the first course of statistics and probability, QM1 and double MEF, okay? Okay. So first of all, some presentation, okay? So I hope that you have received the link toward my webpage. I think so, for everybody, okay? So my name is Christophe Choro, okay? You have my email address, okay, here. Even my phone number, you have everything, okay, my office, okay. In particular, if you have questions, okay, since I have a lot of classes during the first semester, it's better to send me an email to take a meeting, okay. Or it should be also possible to use numerical tools, okay, Skype or Zoom or something like this, okay. So, what is important for you on this web page, okay? On the top right corner, you have QM, okay? And it's okay also for the MMEF students. So as you have received at the beginning of the holidays, something like this, okay, I hope. So you have first the prerequisite of the course. It means that's something that I consider as okay for you. It is more or less just the way to write mathematics, okay, nothing that is really theoretical, okay. But I want you to be, okay, to have some basis concerning theory, okay, concerning combinatorial analysis, that is just techniques of counting, okay, but I will come back on this point on exercises today, okay. I want you to be able to compute sums in this class, okay, because it will be used for discrete random variables, to compute integrals because it will be used for continuous random variable, okay? And I have given to you some exercises in order to train about these notions, okay, with their corrections. So it means that for me, all these first points are okay for you, okay? But I will do some exercises from the summer list, okay, today and the next session, okay? And if I go below, you have all the slides of the course, okay, all the tutorial, all the proofs that I won't have the time to do in class, but that I include, okay, as a material, okay. So you have the probabilistic part and you have the statistical part, okay. Here. And as soon as possible, you will have, okay, here, the videos of the course, okay, that I will. So I hope that it will be in general today in the evening or tomorrow morning, something like this, but you will have it very soon, okay, if everything works. But I have done some tests, so a priori, okay, everything will work, okay, with not that bad quality. Okay, so concerning this course, okay, the structures of the course will be concerning exams, okay, as for the other classes, okay. So you have a midterm exam. So first, attendance a priori is mandatory. So for this here, I don't know really what it means. I will check for attendance at the beginning of each session, except today. Okay, I will start tomorrow, in 2 days. But for the students that are at home, I don't know how to do. I will see. Okay. But a priori, 20%. Okay. For the midterm, it will be 40, and the final 40 also. So this one will be in October, this one will be in December, okay? And on the syllabus of the course, okay, you have the syllabus, okay, at the beginning of this page here. But you have everything that is explained, okay? The link toward all the documents, okay? The detail for each session, okay, course by course, and the exercise we will do during each session, okay. You have also the exams. So here typically, okay, November 10, you will have the midterm exam of probability, okay, in the course 15. And you have the program of this exam that will be from course 1 to 11, okay. So everything will be clear at the beginning, okay. What I may expect from you in the exams, okay, and so on. Okay, so you have all the materials and a priori all the structure of the course I hope that we will be able to do class together as today, but we don't know. So the probability that we have to change the way to work, okay, is not zero. So we will try to adapt, okay? So I think that I will continue my video even if you are not here, okay? So I don't know, but I will do, okay? So don't be anxious with this, okay? To this year we have to be flexible, okay? We will be flexible. You have to be, okay? And I think that it will be okay. Do you have some questions concerning the way we are going to work? So I prefer not to do live sessions because I don't want to deal with technical problems. Mister, my internet doesn't work, okay? I do video in this way, it will be okay for everybody, okay? With the same quality, okay? And the same material, okay? So that's why I prefer to do this. So you know that we have 3 hours each session, okay? A session of course, a session of tutorial, but in fact I will mix them, okay? I will do some exercise, I will continue my course, okay? I will do, okay, not as I want, but as, okay, the course, okay, necessitates. Okay. I won't have the right to print documents at the beginning, okay? So you have to, I have sent it to you an email, so you have. So not on the phone. Very small, okay, so it's the beginning, so we have to be flexible, and I will be, okay, so it's better to print this way if you have, or using, okay, something that is a little bit bigger than, okay, a smartphone, because you will have the slides of the course, okay, so the smartphone is better than nothing, okay, but if you can do a little bit more, okay, it will be better. So I don't know if I will have the right at the moment or not to print. In general I do, okay, but this year, a priori, due to COVID restrictions, okay, I don't have. Okay, so I print for me and not for you. Okay, so if you don't have, so it's not because we have a film of the session, okay, that you don't have to ask questions. You have to ask questions, and my job is to answer. Okay, so forget the camera, okay, and be sure that in a few minutes, okay, we will forget it completely and ask questions if you want. Okay? So I repeat that this is very important and the prerequisites of the course, okay, so that's why I've sent it, okay, few weeks ago, okay, and it's important for you to be okay with this one. I won't have the time during the class to spend time to explain what is the definition of something that is in this part, okay? Questions? No questions? So I propose you to start today, okay, slowly with some little exercise, okay? I will do a little part of the course, okay, with the definition of what is a probability. But before, so 2 exercises from the summer list of exercise, okay? Then a little intuitive introduction to probability, to what is a probability, and then we will start the course. Okay? It's clear? So let's go. So maybe I can do this. I hope that it works. Yes. You will see nothing, so it's for the video, okay, not really for you, because I will try to increase, but yes, it's not that bad. Okay, so I will try to do this, but at the beginning you will see that the video maybe will be a little bit erratic because I have to deal with the computer, the board, okay, and so on, but it will be better and better. Okay. So I want to start with the exercise 5 of the summer list. Okay, so we are, once again, just a little remark, it's not possible for me to switch on the light here because if I do, the video has a bad quality. Okay, so that's why I don't use it. Okay, so the summer list. And the beginning of the exercise 5 of this list. Okay? So typically, okay, in this exercise, the aim is to underline some rules of computations between intersection and union. Okay? In particular, some rules of computation between intersection and union if you deal with a family of sets, okay? Not a finite family, not a countable family, but a general family of sets. So it will be formulas that will be okay in any situations, okay? So I will do the proof of the first because the second one can be done exactly in the same way, okay? But first of all, okay, as a little reminder, just remind what I mean by these notations. So I have a family of sets, okay, indexed by a set capital I. Okay? So for example, if I take for capital I the natural numbers, okay, I have a sequence of sets. If capital I is finite, I have a finite number of sets. Okay, so, but here I can be anything you can think about. So AI is a family of sets. So I know that I can do, and you can come back to the prerequisite of the course, okay, I can do several operations on sets, okay, union, intersection, and so on, complementary set, okay, and here I define the union of all of them and the intersection of all of them. So what is the meaning of being in the union? What is to be in the union of the AI? I am in the union if I am in at least one of them. This is the definition of the union. Okay? So I can define this as the set of the X such that there exists I0 belonging to capital I with X belonging to AI0. This is just the meaning of saying that I belong to the union if I belong to at least one of them. It can be two, it can be three, it can be more, but whatever, at least one. Okay? For the intersection, I am in the intersection if I am in all of them. Okay? For all I belonging to capital I, X belongs to A. So this is the meaning of the union and intersection that are written in the statement of the exercise 5, and it's something that is reminded in the slides of the prerequisites. Okay? So you don't have to be surprised by this because, okay, it's something I have sent it to you a few weeks ago. Question?
What's the notation of the bar?
Such that it means. Such that. Okay? X fulfilling the condition that is after the line, okay, that is for all I, X belongs to A. Okay. So if I know the definition of these two, okay, I am able to do the exercise 5. Okay? And the first question of exercise I will do with you, okay, and the second one, okay, will be an exercise to do at home. Okay, or was an exercise to do at home during the summer holidays, okay, is to prove that B union the intersection of the AI, okay, is equal to the intersection of what? Of B union AI. Okay? So this is some rules of computations, okay, between union and intersection. Okay? So what I have to do, I have to prove an equality between two sets. Okay? So it is possible to do an equivalence reasoning, but I can also, okay, prove this equality between two sets using a double inclusion reasoning to prove that this one is included in this one and prove that this one is included in this one. It's one way to prove equality between sets. You can prove that, okay, one is included in the other and the converse, and in this way you are sure that you have the equality. Okay? So I have two inclusion to prove, okay, if I do this way, I have this one That is the inclusion from the top to the bottom. Okay? So to prove this inclusion, we are going to start with an element that is in this set and prove that it is also in this one. Okay? That's it. So at the beginning, and especially during the first week, okay, I rewrite everything, okay, to be pedagogical, okay. So let X belonging to this one. My aim is to prove that I belong to the other one, okay, using the definition of what is a general intersection. Okay. So what is the definition of being in the union of two sets? So I have this one and this one. So you have to speak louder. So is it possible to close the window because too much noise, okay, as I have said. So if you want to speak, okay, try to speak okay, strongly.
Also belongs B, also belongs
So I have two possibilities, I belong to B or I belong to the intersection. Okay, so let's do the two cases. Okay, so first case, X belongs to B. And we are going to see what happened, that is, we want to prove that we are in this set. Okay, the second case that we will do just after is what happened if I am in the other situation, that is, I belong to the intersection. Okay, so if X belongs to B, I want to prove that X belongs to this one, okay? But what happened? If X belongs to B, okay, I know that X belongs to the union between U and AI, because I am in the union if I belong to at least one of them, okay? So if X belongs to B, in this case, okay, for all I belonging to I, X belongs to B union AI, because X belongs to B. But what is the meaning that for all I belongs to this set, B union AI? If you come back to what I have defined as the intersection between sets, if I belong to all of them, by definition, if I belong to all of them, I belong to the intersection. Okay? So what I have proved the first inclusion in the first case. Okay? The first inclusion in the first case. What happened in the second case? So suppose that now you are not necessarily in B, but you are in the intersection. So what is the meaning to be in the intersection? It means that for all I belonging to I, X belongs to AI. Okay? So I have this. But once again, if for all I belongs to Li, it means that for all I belongs to B union AI, because I am in B union AI if I am in at least one of them. So, for all I belonging to I, X belongs to B union AI, and I can conclude as previously, if for all I belongs to this set, then by definition, X belongs to the intersection of this. Okay. And what I have proved here, I have done the proof of the first inclusion. I have proof for any element in the first, okay, I am in the second set. In order to prove my equality, I have to prove the converse. Okay? So, it's not complicated, okay? It's just use basic definitions about set theory that are considered as prerequisite in this course, okay? So that's why you have some slides, okay, in my website that deal with this kind of properties. Okay, so let's do the other inclusion. this one, from the bottom to the top. And now we are going to start with an element in the second one and prove that it is in the first. Okay? So let x belonging to this intersection. So are you okay with the first inclusion? So I don't want you to be surprised that because it was a summer list with summer corrections, okay, so a priori it's something that is okay for you. Do you have some little questions concerning this, concerning notations? Yeah?
I have some very basic question. What is the N and U? Like the...
What is the?
Start of the let X belongs to the U, N, and then you wrote.
So have you read the slides concerning prerequisite?
No, I haven't.
It's union.
Okay.
Okay? And you have to read.
Yeah, I know.
Okay?
I know.
Union.
No, not this. Okay, so now I understand. I think that, okay, now it's clear for me. I didn't ask that, but in the square,
yeah.
It's the same thing.
No,
okay.
no.
I thought that, okay.
No, it's not the same thing. I want to prove an equality.
Okay.
Okay? Between two sets.
Okay.
To prove an equality between two sets, okay, I have to prove in fact two inclusions. So if you want, okay, I write this way because it's an inclusion from the top to the bottom, but I have a first inclusion between this one and this one, if you want, and a second inclusion here that is from this one to this one.
Okay.
Okay, so I prove by double inclusion, okay, the equality. So it's not the same symbol, okay, I just write it because I have written the things this way, okay, but you have the inclusion here from the top to the bottom, and here the inclusion from the bottom to the top.
Okay.
Okay. Other questions? No? Or for the other, I suppose that I am in this intersection, okay? And I want to prove that I am in the first. Okay, I suppose that I am in the second, and I want to prove that I am in the first. Okay? So what is the meaning of this one? I am in the intersection if I am in each of them. Okay? So, for all I belongs to I, okay, X belongs to B union AI. Okay. And I want to conclude that I belong to the first, that is I belong to B, or I belong to all of the AI. Okay? And to do this, once again, we are going to consider two cases. Because a priori, if I am in B union AI, okay, I am in B or I am in AI. I don't know which one. One of them. Okay? So we are going to suppose first, let us suppose that X belongs to B. And what happened in this case? But in this case it's very easy to conclude because if I am in B, I am in B union the intersection. So X belongs to B union the intersection. Okay? So I have done the job, what I want to do, that is to start from an element to the bottom and prove that it is in the top set, okay? But I have to do it in this first case, okay? The case where X belongs to B. Other case we are going to do, okay, but the opposite, that is second case, we suppose X doesn't belongs to B. I am in B or I am not in B. Okay? Two possible cases. But what happened in this situation if you are not in B? I have an hypothesis, that is that for all I am in B union AI. But I know that I am not in B. So where I am? In AI. I am in the union and I am not in the first. So necessarily I am in the second. Okay? So since for all I belonging to I, X belongs to B union AI, we have for all I belonging to I, that X belongs to AI. What is the meaning of being in all of them? It means to be in the intersection. So X belongs to the intersection of all the AI. And if I am the intersection, it means that I am in the union of B and the intersection. So X belongs to B union the intersection. Okay? And what I have done, I have proved for this second inclusion that anytime I start from an element of this set, I have proved that it belongs also to the first one. So I have proved this inclusion. I have proved the first inclusion and the second, so I have the equality between sets. Okay? So it's a rule of computations we have proved, okay, and the rules of computation that we will be able to use now. Okay? The fact that B union a general intersection is equal to the general intersection of the B union AI. Okay? And in the list of exercise, you have the analogous, okay, if you replace intersection and union, okay, I want to do the correction because it's exactly the same kind of reasoning, because you have the correction in the list of correction in my website, okay, but I think that if you don't have already done this one, okay, it's a good exercise to see if you have understood this reasoning, to try to do the second part of the exercise. Okay. So I have a rule of computation between, okay, B, the union, okay, and the intersection of a general family of sets. Okay. And you will see that in general, okay, when we will do exercises, okay, sometimes I will use the results of the exercises in my course. Because, okay, once we have seen something, I suppose it to be true, and so I will be able to use. Okay. Do you have some questions? Is it okay for you? Is it complicated? Is it hazy? Is it boring? So boring for sure. But it's the beginning. Okay, so at the beginning, okay, I just practice, okay, with mathematical notations for the moment. Okay, it's my job to do this week. Okay. Is it okay? So it's really important to spend time at the beginning on this basis, and that's why I repeat that I have done the documents for the prerequisite. Because, okay, all the maths we are going to do after will be written using these prerequisites. Okay? And I want to be able, when we are going to start the probabilistic part or the statistical one, to come back to the definition of everything, of course. Okay? So spend time at the beginning with this, okay, if you are not okay. So that's why at the beginning, okay, I will go slowly, especially this week, okay? Without introducing too much new things, okay? So are you okay? So I have a very small board, as you see. Okay, so I need to erase and erase and erase. Okay, so if you are okay, I will erase. Okay for everybody? So you have the video if you want to come back on a point or an explanation. That's why, okay, you have these two. Okay, so I erase everything, okay? And I want to do a second exercise. So for the quality of the video, okay, it's very important to erase in a good way. Okay, so that's why I will spend time, okay, erasing, okay, the best I can. Or you will have, okay, a video with a cloud of clay. Okay? That is not that okay. Okay, so let's continue with the exercise 8, this one, okay? in this exercise 8, okay, I introduce a notation that is the notation of what we call an indicator function, okay? Something that will be useful, okay, in the parts of probability and also in the part of statistics, okay? It will be, as we will see next week, okay, one of the simplest examples of what we call a random variable, okay? So, I consider a set capital E. So it's the exercise 8 of what I have called the summer list of exercises. Okay. So I consider a set capital E, excuse me. Okay. That is for me in this exercise, okay, the biggest one. The one in which all the other are included. Okay, so it's what we call in general the universe. The biggest set we are going to consider, okay? Universe. Biggest one. Why I do this? Because, okay, any capital A that I will consider below will be a subset of capital E, okay? And I consider A included in capital E, meaning that A is the subset of capital E. So this is, to come back to your question, this is the notation of inclusion.
Okay.
This one, okay? Notation of inclusion. Okay. So I have a subset of E, and we are going to define what we call the indicator function. The indicator function, okay, is just a mapping, in fact. A mapping that will allow you to know if you are in A or not. So, in other words, so it's a definition here at the beginning of the exercise. Definition. So what we call the indicator function of A, okay, so it's a one with this double bar here, okay. Indicator function of capital A is a mapping. Okay, so the notation I used, you do a one, okay, in this line. The way you write. Indicator function of Y is a mapping from what? From E into 0 or 1. It's a mapping that only takes two possible values, 0 or 1. Okay? A very basic one. 0 or 1. When it is 1, it is 1 if x belongs to A. If you have here an element in A, the indicator function of A at the point x is equal to 1. Okay? If x is in A, the indicator function is 1 and 0 otherwise. So in other words, okay, if you know this mapping, it means that you know all its possible values. But you are going to be able to know if an element is in A or not. To check this, okay, you will have just to check if the value of the function is 0 or not at this point. Okay? So it's a mapping with a value equal to 1 if I work with an element inside the set capital A and 0 otherwise. Okay? So the knowledge of the set capital A or the knowledge of the mapping are totally equivalent. So it's a mapping, okay, in the classical that associate to any x two possible values depending if I belongs to A or not. Is this definition clear for everybody? Yeah? So I repeat, and it's not because we have a video of the course, okay, that you don't have to ask questions. Huh? I have a little bit of experiment, okay, and I remind that few years ago, for different reasons than COVID, okay, we have done this, and I had no question during the first semester. Not because, okay, everything was okay for the students, just because they don't want to be on the video, but don't worry, okay, it will be only me in the video. Okay, so if I do mistakes, it will be me on the video, not you, okay? So ask questions, okay? Okay, so I have this. And in fact, we are going to prove some relations, okay? So I won't do all of them, okay? But I will do few. Okay, so typically, let's start with the small a. So I consider two sets in the question small a. Okay, I consider two sets, capital A and capital B, and I want you to prove an equivalence. That is, a set A is included in another set B, if and only if the indicator function of A is always less than the indicator function of B. Okay? Why not? So just a remark before to do this. So I have an equivalence to prove. It would be possible to prove it by double implication. Okay? To do one side and the other one to have the equivalence. Okay? Just the meaning of this inequality here. It's an inequality between mappings. Okay? So just be okay that this one means that the inequality holds for any x in capital E. For all x belonging to E, indicator function of A x is less than the indicator function of B x. Okay, mapping F is less than mapping J, if and only if for all x, F of x is less than J of x. It's exactly what I write here. Okay. So we are going to prove the equivalence. We are going to prove the equivalence. So I have two sides. So let's see what happened for this one. Okay. I suppose A included in B, and I want to prove that every time the indicator function of A is less than the indicator function of B. As you can see in this definition, the values of an indicator function depend on the fact that I am inside or not the set. So this one is 1 if I am in A, 0 otherwise. This one is 1 if I am in B, 0 otherwise. So in fact, if I want to prove this one, I have to consider cases. And what are these? These cases, okay, they are x belongs to A, x doesn't, x belongs to B, x doesn't. So how many cases I have to consider in fact? 4. I have two conditions with two possibilities each time, okay? So a priori, my hypothesis will be A included in B. I want to prove this one, so it means that I want to prove the inequality for any x. Okay, since we know that the value of an indicator function depends on the fact that I am inside or not the set, okay, we are going to consider the 4 possible cases. So 4 cases. Which one? X belongs to A, X belongs to B, X belongs to A, X doesn't belong to B, X belongs to B and doesn't belong to A, and the case where both doesn't belong. Okay? So first question, I said that I have an hypothesis, that is this one, A is included in B. And I said that from this hypothesis, in fact, I have one of these cases that is not possible. Which one? A second. It's not possible for me to be in A and not to be in B because A is included in B. So this one I don't have to do. Impossible. By hypothesis. Okay? So I don't have to do it, okay, because it is impossible, because A is included in B. Okay? So I have only to do the 3 remaining ones. Okay? Okay, so for the first, I am in A and I am in B. What is the value of the indicator function of A at x, and what is the indicator function of B at x? What are these values? 1 and 1. 1 and 1, so I can write this one. Okay? Means that in this case my inequality is okay, because both of them are equal to 1. Okay? So the second case is impossible. For the third one, I am not in A, I am in B. Once again, what is the indicator function of A at x and what is the indicator function of B at x? What is this one? 0. This one 1. And once again, I can write my inequality. Okay? And finally, you have understood, both of them are equal to 0. And so once again, I can write my inequality. I have proved that in all the possible situations related to my hypothesis, then I have the inequality I want. So I can say that A included in B implies indicator function of A is less than the indicator function of B. Okay? We are going to prove the converse. That is, if I have this inequality, let's prove that I have this inclusion. Okay? Are you okay with this reasoning? So the only question is why I consider cases. And my answer is because in the definition of an indicator function, I have cases. If I want to know exactly what are the values, I need to check if I am in A or not. Okay? So if I want to have the real value of the indicator function, I have to consider cases. Okay? So I have proved here the implication from the left to the right. Let's do the converse. So in this case, my hypothesis is that I have this inequality. My hypothesis is this one. And what I want to prove is that A is included in B. So to prove that a set is included in another one, I start from an element in A and I want to prove that it is in B. Okay? It's the reasoning I have to do. So my objective is to prove that A is included in B. I want to prove this. So let's start with let x belongs to A, okay, and I want to prove that x is in B. Okay, so if x belongs to A, what happened for the indicator function of A at the point x? So in this case, the indicator function at the point x is equal to 1. But I have an hypothesis. That is this one. Okay? I know that the indicator function of B at the point x is greater than the indicator function of A at the point x. This one being equal to 1. So what you can conclude about this one? But an indicator function takes values in 0 or 1. So if you are greater than 1, you are 1. Okay? So the indicator function of B at the point x is equal to 1. And since it is equal to 1, I can conclude that x is in B. Okay? And it's exactly what I want to prove. Starting from an element x in A, I have proved that I have an element x in B. Okay? So Do you listen to me correctly with the mask? Okay? If you want a picture of me without the mask, I'll go on the web because I'm not sure that until the end of the semester, okay, I think that you will see me with this one on. Okay. Yeah?
How does having one element in A and the same element in B prove that A is in B? Am I reading that wrong?
No. So, the meaning of this one,
Yeah.
it's the definition of this inclusion,
Yeah.
is that any element here has to be here.
Right.
It's the definition, so it's exactly what I prove. I start from an element here and prove that it is in the second one, so I have exactly the inclusion. It's the definition of the inclusion itself. Okay? To prove that a set is included in another one just means that any time you take an element in the first, this element will be in the second one. If I do a little picture, it's something like this, okay? I have A and B. All the elements in A are in B. Okay?
Isn't it possible that what we proved now, it can mean that as well, set B can be set A otherwise? Is it possible as well?
I don't have understood the question, so please repeat.
Okay, since X belongs to A and X belongs to B, how do we know that B is not a component of set A?
So,
Can it be like
several questions. So first, okay, what is the meaning of being a component of the set B?
component, but since A is subset of B.
Yeah, I am in this situation.
Yeah, is it like because of the hypothesis we concluded that, or we can conclude that B is subset of A as well?
No, not here.
No. Okay.
No. My hypothesis is this one. Huh?
Okay.
I said that from this hypothesis, from this inequality, okay, I can prove this inclusion. If you are still in this hypothesis, it won't be possible for you to prove the converse. It doesn't work. If you want the converse, okay, you need to have the other inequality. If you want the equality between the set, you need to have the equality between the indicator function. Only in this case, okay? So you have simply this inclusion, A included in B, and not the other one up here.
So if the exercise it would be subset of A, then we would prove that by this B is subset of A, right?
If you want to prove that B is included in A, you will start with an element in B and prove that this element is in A. But with my hypothesis here, it's not possible for you to do this. Other questions?
The reason why we're only considering 1 and 0 is because we're using indicator functions?
No, it's not because we use indicator function, because by definition of an indicator function takes values in 0, 1. I have only two values, 0 or 1. Okay, that's why we can do several conclusions. Typically, if you have a function mapping that is greater than 1, in general, it doesn't imply that it is equal to 1. But if you take only two possible values, 0 or 1, if you are greater than 1, necessarily you are equal. Okay, it's not a generality, but something that is typical to my situation here. Okay? Other questions? No? Well, maybe I will make you work a little. Okay? So try to do by yourself the beginning of the question C of the exercise 8 here. Okay? The relation with the indicator function of the union. Okay? So, may I erase if you don't have questions? I can erase everything. Yeah, I erase. So what I want you to do now, okay, by yourself, I will give you 5 minutes to do. Okay, if you have understood my previous reasoning, okay, you will have it. Very basically, I want you to prove that the indicator function of the union, okay, is equal to what is written here. That is the indicator function of A plus the indicator function of B minus the indicator function of the intersection. Okay? give you 2 minutes to do, in fact. If you have understood the principle, it's very basic, okay? I know what are all these mappings, okay? It's mappings with values 0 or 1, depending if I am in the set or not. So you have to consider cases in order to do. Okay? So let's do. Okay? So try to do, and when I say try to do, you take a pen, a paper, and you try to do. Okay? Not just looking at the board. Okay? So a priori, I don't know exactly because I have said that we will have to be flexible, but a priori, if this here is a classical one, for my exam, okay, you will just need a pen, the paper. No calculator, no phone, no documents, okay, a priori. If it changes, I will say it to you, but a priori it will be this way. So we'll just check that everything is okay with the video here. Here it works. It works, but without the slides. I have sent it an email to you on Friday, if I remind. Everybody has received it? Huh? Well, to be sure that my mailing list was okay. I will use it a lot. Huh? So I have to prove an equality between two mappings, okay? So I have to prove that I have this for any x belonging to capital E. Okay. So if I do a little picture of the situation, a priori, okay, so I have no hypothesis. So my capital E is the big set, the universe, okay? In general, we call it omega, but in this exercise, it is called capital. Okay, I have two sets without any kind of hypothesis about them. So if I do a picture, okay, the more general situation is this one, AB. Not equal, but with an intersection that is not empty. Okay. Just a little remark concerning the use of the pictures, okay? Keep in mind that in mathematics, okay, a picture is not a proof. You can use a picture in order to try to find a good proof, okay, but if you do only a picture in general, picture is not a proof. So I use it to help me, okay, and after I have to write. So I am in this situation. So a way to do, if you have the principle, it's very basic to do. Huh? What is the idea? Idea? You have an idea?
Maybe you can see four cases.
Yeah, once again. And what are these 4 cases? I am here, I am here, I am here, I am here. The 4 regions, okay, that are delimited by these 2 sets. It's exactly what I have done in the previous question, okay, to prove the first implication. Okay, so we are going to consider the 4 cases. And in this case, I have really 4 cases. In the previous one, okay, I had already 3 cases because I suppose that A is included in B. Here, I have no more this hypothesis. So I have really to consider the 4 cases. Okay? So, let's do it again. And see what happened. Okay. Okay, if I am in the first situation, we are going to see what are the values of each member. Okay, so I will do it first in this way. So what is this one here? I want because, okay, I am in the union if I belong to at least one. I belong to at least one because I belong to both. Okay. So 1. What is this one? What is this one? 1. And what is the last? 1 also. Okay, because I am in both, so I am in the intersection. Because I belong to both of them. And so, each of them being equal to 1, okay, but I remark that 1 can be written as 1 plus 1 minus 1. And I have my equality. Okay? And if you have understood the principle, I can do it easily for all of them. So just writing this one, okay, instead of doing all the steps, okay, here. So if I am in A and not in B, where I am in the union, I am in A, I am not in B, and I am not in the intersection. Because to be in the intersection, I have to belong to both of them. Okay? So I can write the following. 1 is equal to 1 plus 0 minus 0. Okay? Seeing what are all the values of these indicator functions. Is it clear? So I continue with this one. If I am in B, not in A, I am in the union, I am not in A, I am in B, I am not in the intersection. So I obtain 1 is equal to 0 plus 1 minus 0. And it works. Okay? And finally, if I am none of them, I am not in the union, I am not in A, I am not in B, I am not in the intersection. Okay? So you see that a priori, when you want to prove equality between indicator functions, okay, you have to consider cases. And in this way, you are able to obtain a relationship between them. Okay? So I will use, okay, this notion of indicator function a few times in this course. Typically, okay, it will be the more basic example of what we will call a random variable. But we will see this later. Okay. Questions? So I have done the job considering cases. Okay. So I think that for the exercise of the summer list, it will be okay for today. I will do other ones, okay, during the next session, in particular to do some reminder concerning induction reasoning. Okay. So if you are okay, I will erase everything here if you don't have questions, okay? And before to really start the course with the definition of what will be a probability for us, before to show you the theoretical definition, okay, I want to remind you what is the intuitive notion of what we call the probability on a concrete example. Okay, but very basic. Okay? Yeah.
Just going up as a source, first then do the integration by definition, and then we just verify the right side.
Excuse me, you have to speak okay strongly because I don't understand.
If you just see, if you just calculate the indicator function for A and then minus the intersection,
Yeah.
we are just verifying the result.
Yeah.
So should we do the other side?
No. What I have to prove? I have to prove that I have this equality. Okay? I have proved here that the equality is okay for the only 4 possible situations, so it is okay every time, so it is okay.
But how does it prove? Like you are just verifying.
No, I don't have verified, I have proved. Okay? What I have proved? I have proved that this equality holds every time for any x in the space capital E. In order to prove this, I just say that in order to prove that it is okay for any x here, I prove it, okay, just, okay, differentiating between some particular regions, okay, and at the end I have done the job for everybody. It's just what I have to prove. I have proved that the equality holds. What is the meaning of the equality holds? It holds for any x, and it's exactly what I have done here. It's my picture. So my picture is not a proof, but in order to just say what I have done, okay, to prove this equality, I have to prove that it is okay for an arbitrary x here. Okay? Are you okay with this?
Yeah.
So what is your problem exactly?
Like for me, when I do something, I can see if it is true in both sides. And it seems that I'm just.
If it is, excuse me.
If it is true for both sides, then it seems to me that.
No. You have an equality between numbers here. To prove that, I don't know, 2 is equal to 4 over 2, you can prove it directly, okay? It's not necessarily to do in each direction, okay? It's an equality here, okay? You have mappings, okay? If I prove it for any x inside the domain of definition of this indicator function, okay? I prove the equality, point. What will be the converse? You don't have the converse here.
I will go by definition. I will go by definition.
Of what?
Indicator function for the union.
It's exactly what I have done here. I have used deeply the definition of the indicator function of the union, of the indicator function of A, the indicator function of B, the indicator function of the intersection. I have used, of course, the definition to prove that I have the equality. I have used it. Okay? I use the definition in order to prove that I have this equality, because if I don't choose the definition, I can't prove anything, yeah, for sure. Okay? So, it is not totally clear in the way I've written, but here, and here, I have used what are the definitions of each term here. Okay?
Could we eliminate case 2 or 3
No.
by saying that since A and B are any 2 sets, the second one is without loss of generality?
No. Why? No, because when you see the situation, you have to consider the K2 is this one,
Yeah, but
and the K3 is this one.
since A and B are 2 any sets,
And so,
case 2 and 3 are equivalent, so without loss of generality.
you say that if I do this one, I can. So,
it
it's
implies
not-
it's equivalent.
equivalent, not really, but yes, I agree with you that a priori for this one here, you have a kind of symmetry between the way to write. I am agreed that if I want to go very quickly, okay, I can say that instead of doing both 2 and 3, I can do only one of them.
Yes, it's because.
But
A and B are
you see that the time it takes me in order to write is 2 seconds. Sometimes it's very interesting, okay, in order to short a proof, but here, not really, but you're right. I have symmetry, so if you want to remove 2 or 3, it will be okay. Yeah?
On veut une fenêtre
Et j'ai trop de bruit, je suis filmé en fait. Juste c'est une tout de suite. Donc, ouais, donc là je suis. I hope that I don't have done mistakes. We'll see. So it's the first test, okay, so a priori it works here. I hope that it will work for what I have done previously. Okay. Okay. So let's go to the slides, okay, but at the beginning, okay, so I will do this. I just check, I am sorry, but at the beginning, okay, I have to see if it works or not, okay. And I hope that it will be okay. Have you already tried to see a video on the API or something like this? No? I will do it tomorrow morning, I think, okay, for this one, okay, have a look if it works or not, okay. The problem is that I won't be able to do it another time, okay? But I will be better and better for... Okay, so this one works, okay, so before to do what I want to do today for the course, just give you some intuition of, okay, what is the probability, because you will see, okay, the real definition in the next slide, okay. But first of all, so let's see a concrete example, okay, the one that I will use a lot of times. That is, I roll a dice, okay. Let's say that I roll a classical dice. So what are the outcomes of this experiment? If it is a classical dice, 1, 2, 3, 4, 5, or 6. Okay? So I have a set that I will call the universe that represents, okay, the outcomes all of my experiment. Okay? So here I roll a dice, so I obtain 1, 2, 3, 6, 5, 6. Okay. In the first situation, I suppose that I have a fair dice. Okay? What is the meaning of being a fair dice? It means that each outcomes, okay, has the same frequency to occur. So if I do a little table, okay, I have my outcomes here, so 1, 2, 3, 4, 5, 6, okay? And in the case of a fair dice, what is the frequency for each of them? 1 over 6, okay? And I see that the sum of all of them here is equal to 1. Okay? I have here positive numbers with a sum equal to 1. Okay. And typically, in this situation, if I ask you what is the probability to obtain 1, what you will tell me? 6. If I ask you what is the probability to obtain 1 or 2? So here it will be, let's say, 2 over 6. Or that is 1 over 3. Okay? And in fact, more generally, if I have A that is included in omega, that is, if I have a subset of my universe, that is the set of all the possible outcomes, okay? Well, I can define P of A equal to the number of elements in A over the number of elements in omega. So this is a definition that was introduced in the slides in the prerequisite. It just represents, okay, the meaning of this one means that the number of elements in A, the number of elements in omega, okay? So I can define it this way. So if I come back to my two little examples, here I have only one element in this set, 1. So it is 1 over the number of elements in omega. In omega I have 6 elements. Here, how many elements? 2, okay, over 6, that represents 1 over 3, okay? So if you are in the situations, okay, in real life, where this situation is fair, in the sense that each possible outcomes appears at the same frequency, you have, and it's exactly what you do in general in real life, to compute probabilities, you have just to compute the number of elements, okay, in sets, to count, okay? So that's why in the prerequisites, okay, you have a family of slides that are called, okay, combinatorial analysis, that are just techniques of counting, how to count, okay, how to count in a clever way. Okay, so I have this. It's a natural way in order to define a notion of probability in a fair case, okay, in the real life. Here I have taken the example of dice, you can take the example of what you want. I choose randomly a student, okay, in this room, okay, you have a probability and so, okay? And I can compute, okay, some probabilities. Okay. If I have this definition, this basic one, related to this very, very particular situation, okay, I can see that I have some particular properties for this definition. What is the probability of the empty set? This is the notation, also introduced in the prerequisite. Empty set, the set with no elements. What is the probability of the empty set with this definition? 0. What is the probability of the universe? 1. What is the probability of A complementary? Complementary set is omega minus the element of A. Okay? And if I take P of A union B, do you have a formula for this one? For example, if I take an example in order to show you why I have this one, okay? Suppose that you want to obtain, let's say, this one. Probability of 1, 2, union 2, 3. Okay? So I can do, so first I know that it is the probability of 1, 2, 3, so it will be 1 over 2. But whatever, suppose that I want to use this formula. Okay? So it's the probability of 1, 2, that is 2 over 6, plus the probability of 2, 3, that is 2 over 6, minus what? Minus the probability of what they have in common, that is the element 2. I have one element in the intersection. And you recover here exactly 1/2 with this one. Okay? So if I repeat what I have said, I have a basic way to define the probability in a situation where I have something that is fair, let's say. Okay? This definition deals with counting elements in a set. Okay? if I use the definition, I can see basically from the definition of this n, okay, how to count elements in a set. I have these properties here. In particular, if they are disjoint, that is the intersection is empty, okay, I have the probability of the union that is equal to the sum of the probabilities, but in the case where the intersection is empty. Okay, so I have this. The problem of this situation is that, okay, if I want to model more complex situation than rolling a dice, okay, it is not always possible for me to use this kind of nice formula. Okay? I have to extend it a little. Let's consider a second example, okay, that is of the same type for the moment. Once again with my dice. And let's suppose that my dice is not a fair one. Why not? Okay? Suppose that it is not a fair one, so I am in an unfair situation. But still in the case of my dice. If I do once again my little table, okay, I have my 6 outcomes. And here I see that I have a really unfair dice, okay, supposing, for example, why not, that frequency of one is 1/2, okay, and for the other, okay, the same for all of them. If I do the sum once again, okay, I obtain 1, okay, I obtain. Let's do the same here, okay? If I ask you to compute P of, let's say, 1. One over 2. P of 1, 2. I do the sum. Okay. Okay, so I have this. And now I see that contrary to the previous case, okay, I don't have the same numbers. Here I have different possible numbers, okay. And I have a way to extend this definition in this situation. Okay, what can I say? I can say the following. So if I define, okay, this frequency by F1 here, this one by F2, F3, F4, F5, F6, okay? If I want to compute P of A, how to compute it? Okay, it's exactly what you have done here. But you will do the sum of all the frequencies, okay? So let's write it this way. It's that, okay, I belong to A. This way. So what I do, I have elements here. And this formula just means that I have elements in capital A. In order to compute the probability of this set, I just do the sum of the frequencies related to the element of capital A. Okay? If I is in A, I do the sum of all the frequencies. So for example, if I have this one is inside, 2 is inside, so I do the sum of the 2 first frequencies, okay? If I want you to compute the probability of 2, 4, and 6, for example, you will do 1 over 10, 1 over 10, plus 1 over 10. Okay? And what is interesting to see with this definition is that even if I am not in a fair case, but in an unfair one, okay? In general, it's what happens in real life. For example, if you flip a coin, in general, you don't have a perfect coin, okay? For many kind of reasons. But if I use this definition here, I can see very basically that the same properties occur. I have the same properties. Probability of empty set 0, probability of omega 1, probability of complementary set 1 minus the probability, and probability of the union P of A plus P of B minus P of the intersection. So, with these two examples, okay, in general, you are able to compute probabilities, okay, for basic situations in real life. Okay? We are going to do some little exercise in order to underline this situation. Okay? And after, I will pass to the true definition of a probability that seems to be a priori far from this one. Okay, but this one is just a very particular case with these natural properties, okay, of what we will consider in the following as a definition of what is a probability. Okay? But before to do this, okay, we are going to do once again some exercise of the list. Okay, so I just check that everything is working. Okay, yeah. So I come back to my list and we are going to do some exercise with cards. Okay, that are which one? Excuse me. This one, 28, okay, and 29. Okay, so we are going to do 28 and 29, and I just take a break of 10 minutes before, okay? So I will just... Okay, so just to illustrate the intuitive notion of probability that I have reminded here, okay? Let's do two little exercises, okay? The 28 and the 29 of the summer list, okay? So I consider that I have an ordinary deck of 52 cards. Okay, so first what I mean by ordinary deck, because it depends on where I am, okay? So for me, an ordinary deck could be something with what we call 4 colors. Be careful, the colors are not black, red, yellow. Okay? So, an ordinary deck four colors that are spade, club, diamond, and what? Earth. Okay? It's what I mean by 4 colors. One of them, okay? Spade, club, diamond, earth. Okay? So I have what? Concerning the real colors. Spade, black. Club, black also. Diamond, earth, red. Just be careful, I don't want to make confusion. Okay, club is black here, and diamond is red also. Okay? Be careful, you have colors in the common set and color in the sense of the deck. Okay? And for each color, okay, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? I have Jack, Queen, King, and Ace. Okay? So you have here 13 multiplied by 4, I have 52 cards. Okay? And if I have an ordinary deck, okay, I can suppose that if I choose one card, okay, among them, okay, I have something that is, as in the previous situation, that is something that is fair. Yeah?
Isn't the ace the one?
Ah, yeah, right.
Of course.
Okay.
Thank you.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay.
Thank you.
I have this one. So when I draw a single card in my deck, okay? I have a universe, omega, that may be one of these cards, okay? And how many elements in the universe here? 52. Okay, so omega is the set of all cards. N of omega is equal to 52. Okay, so if I want to compute probabilities, I will just have in this situation to compute the number of elements in sets. Okay? First question here. First question. What is the probability that a chord is a king? Write it this way. So first it is over 52, and I have to count the number of kings. How many? 4. 1 for each color. Okay? I go quickly, just to remind. Find the probability that the card is a face card. What we mean by face is this one.
Well, divided.
So I have 3 by 4 divided by. You can simplify, but it's not my problem. Okay? So I have 3 by 4 divided by. Okay? Find the probability that the card is a red card. Half are black, half are red, okay, but if I do the computation using the definition, it is 26 over 52, that is equal to 1/2 for sure, okay? Tell me, it's basic, so if you have questions, you ask me. If you don't have, I continue. Find the probability that the card is a red face card. Red and face. So how many? So I have Jack, Queen, King for the diamond and the earth. So how many? 6. Okay. Okay. And finally, find the probability that the card is a red or a face. So if I write it, okay, using mathematical symbols, okay, or is the union. So I want here the probability of red or face. We have seen together previously that we have a probability for this. Okay? I can use the fact that with the elementary definition, the probability of the union is equal to P of A plus P of B minus P of the intersection. And in fact, I have everything. I have P of red, P of face, and P of red and face. So I have everything, I just have to apply this formula. Red, this one, face minus P of red face. Okay? So here it's really basic, but what interests me in this, okay, it's not the final number you will obtain, okay, it's just the way you obtain it using this formula. And because, okay, in the 3 previous questions, I have computed each of the terms here. Okay? So I have this one. Here it's the case where I draw a single card, okay, in my deck. Okay? This way. Questions? So here, to do this, in fact, I don't read a course about theory of probability. Okay, I count. And it's in general what you do, okay, in real life for very basic situation if you want to find the probability. The number of success over the number of total probabilities and total possibilities, total outcomes. Are you okay? with this one? Nothing to say. I complexify a little, not that much, okay? In exercise 29. What I do in exercise 29, I don't choose simply one, but two. Okay? I don't choose simply one, but two. So I repeat, do you have some question concerning the exercise 28? Is it okay for everybody? If it's okay, I erase. Because I have a single board. Because I use the cam. In general, okay, in previous year I used all the other boards, okay, but with one webcam it's not possible to use more than one. Okay? I erase. Okay. So for this one I can keep the same. So here I don't choose a single one, but two. And the problem is with two, contrary to what happened with one, is that, okay, I can do it in several ways. If I choose two, I can, for example, choose the first one, put it back in the deck, and choose another one. One possibility. Okay. I can choose one, okay, keep it, and say that it's the first I choose another one from the remaining deck, okay? So I have taken into account the order, okay, but without repetition in this case. But I can also take both of them at the same time, it's a possibility. Okay, so when I choose several cards or even several elements in a set, okay, in fact I have several possibilities, okay? Several possibilities depending if I take into account the order. May I speak about a first choice, a second choice, okay? And depending on the fact that I allow replacement, repetitions or not, okay? Okay. In this statement here, it is, let's say that clear, yeah, what I have to use. And all these cases, okay, it's something I do in the prerequisite concerning, okay, techniques of counting and combinatorial analysis. Okay, in the slides in the prerequisites, you have situations, okay, and I remind you the way to count in all these situations. So what happened for this exercise here? So if I want to see what happened for the exercise, okay, I have to read the statement. Okay? Okay, and if I read the statement, first I can see that order is important. Okay? So I have to take into account the order here. Okay, a priori. Because I speak into the statement about first and second. So it means that, okay, here I can do this from the statement. And if you have a good statement in general, okay, you don't have ambiguity with respect to the choice you do, okay, but it depends. So here, if I have a look on the third question, the first is a spade, the second is an earth, okay, so I have to take into account the order, and I have no choice about this. Concerning the fact that I do this with replacement or not, okay, it is not that clear here. Not that, okay? So I would suppose that it is the case, because in general I take one, I keep it, and I take another one. Okay, it's what I do usually, but it's not the only way to do. Okay, so this one is from the statement, okay, and as an hypothesis, okay, I suppose that it is done without repetitions. You can do the same exercise, okay, so for the order I have no choice and no ambiguity, but you can do the same exercise supposing that it is with repetition, meaning that once you get one card, you put it back in the deck, okay, and see what happens, okay? But in general, the true situation and the one we use in the real life is this one, okay? I do it with order and without repetitions. So now I have a new universe with respect to the previous situation, because in the previous situation I just draw a single card. Now I draw 2 with order and without repetitions. Okay? If I want to compute probabilities, the first thing I have to know is how many elements I have in my universe, how many outcomes. Okay? So how many elements in the universe in this situation here? So I have to choose first a card, okay? Order being important, and then another one without allowing repetitions. How many possibilities? If you want to look on the prerequisite, okay, it's something I have defined in this.
52 times 51.
So it's what we call A252. And what is this A252? It's exactly to choose 2 among 52 with order and without repetitions. And I am agree with you that the value of this symbol is simply equal to 52 times 51. More generally, we define A and P. It's what we call arrangements, okay? That are different from combinations. Okay? And I repeat that everything is explained in the slide and considered as prerequisite for this course. I have here, okay, n factorial over n minus p factorial. This is the definition of this one. It's the product of the n first natural number divided by the product of the n minus p first natural number. And here in this situation, it's 52 times 51 times and so on, okay, divided by 50 times 49 times 48 and so on. So I have only these two terms. So this is the number of elements in my universe. Choose 2 among 52, taking into account order and without repetitions. Okay? So I repeat that. I can show you. If I come back to these slides here, okay, that are the second part of the slides for the prerequisite. Okay, you have what we call sampling models. Okay, and I define, okay, what happens if I do the job without replacement and with order, and you have at the end, okay, exactly what I have written here. Okay, so it's not that new, okay, it's what I have considered as prerequisite. Okay, and it is explained in the slides here. So let's come back to the exercise. Okay, so if I have a look on the first question, I am interested in the probability that both are space. What is this probability? So I want 2 space. So it means that for the first I have to choose one of the space, okay, and for the other one also. I know that it will be over 52 times 51 because it's the number of elements in my universe, okay? And how many possibilities to choose 2 spaces? And I remind you that my hypotheses are that I do this without repetition and with order. So how many possibilities to choose 2 spaces? So 13 times 12, okay? So it's what I call here A213, to choose 2 among 13 with order and without repetition. That is exactly 13 times 12 over 52 times 51. Okay? Choose 2 among 13. I have space here. I choose 1. I have 13 possibilities. Okay? If I choose another one, it remains 12 possibilities. The first one was a spade. Okay?
Yeah, I mean, I just
one comment, because that's the way I was thinking about the exercise. I wasn't using those A's. I was just thinking, okay, what's my possibility of taking the it's 13 times divided by 52, and then what's my probability of taking another one, and I multiply, and from the independence, that's basically...
So you have to be careful. Yes, I just be careful because I have no more battery, so I have to use. But be careful concerning this. So it's right what you do, but why it's right, why it's okay? Because in fact, from the first drawing to the second one, you change the universe.
Yeah.
Okay, so what I do, I consider directly a universe of taking two cards. And in fact, what you do in reality is something that is more related to something that we are going to see next session, that is what we call conditional probability. Because, okay, you do first something, and then you change the universe, because you know that you have drawn a spade, you change it, and you do a new computation that is, okay, in some sense independent, but with this new universe. Okay? So be careful, because in other kind of situations, okay, fine. It's okay, but think about changing the universe. Here it's equivalent. But I am not sure that for more complex situation, okay, you won't do mistakes if you do like this. Okay? But a priori, okay, give rises to the same results here. But okay, if you want to separate in both parts here and here, it means that you change the universe, because the deck, when you have chosen already one card, you have a new deck with only 51 cards. Okay. Oh, it's okay, so I won't say no, but be careful. Okay, question B. Find the probability that the two cards have not the same color. So keep in mind that same color means both spades, both club, both diamond, both heart. Okay? Do not have the same color. So of course there is a link with what I have done previously. Previously I compute the probability that both are spades. Okay? So both are spades is something that is in relation with, they have the same color, in the sense of color is one of them. Okay? So why I make this remark? It's because sometimes when I want to compute the probability of a set, it's better to compute the probability of its complementary set. Okay? Repeat. To compute the probability of a set, sometimes it's better to compute the probability of its complementary set. Sometimes, not every time, okay, because sometimes the complementary set is easier to describe than the set itself. And it's typically what happened in this situation here. Because if I have a look on what I have done here, I have done the job for both are spades. If I ask you the question, what is the probability of the two have the same color? What is this probability? The two have the same color. Well, it's something I have already done, in fact, more or less. Here I have done the job for both spades. But what is the meaning of the two have the same color? It means that they are both spades, or both club, or both diamond, or both hearts. Okay? I can write it this way. Both spades plus the probability of diamond. Okay? And in fact, I have already computed each of them because it is just this one. If I change the color, it doesn't change the probability I have already computed. So for this one, it is just 4 times what I have previously computed. That is this one. Okay? And so the probability I am interested in is what? I am interested in the probability that they have not the same color. It is the complementary set of the set they have the same. So the probability that interests me, okay, in relation with what I have computed here, the probability of don't have the same color is just, I use the formula in relation with the complementary set. The probability of the complementary set is 1 minus the probability of the set. So it is 1 minus what I have previously computed here. That is 1 minus 4 times 13 times 12 over 51. Okay? So it's not the only way to do. You can try to do it directly, describing what is the meaning of they don't have the same color. Try to do and check if you obtain the same results. Here, okay, I prefer first to compute the probability of the complementary set because I have already done this job, okay? And I know that I have done the main part of the job when I have computed this. The main part of the job. Okay. Yeah? For which? For this one here?
Yeah, no, for the last one.
So you can do everything you want. The only thing is that it has to be clear. Okay? And in fact, when I will correct your copy, the only question I will try to answer is that, okay, if I see an explanation, okay, my only criteria will be, okay, if I propose this solution to a student, okay, is it okay for him or not? If it's not, I consider that it is false. Okay? So, why not? Okay? So we have to discuss more deeply concerning what is the 26, okay? But you have to explain. If you just write me, okay, A2, 26 without explanation, you won't have the points for sure. For sure. Okay? So I don't say that it's not possible, maybe it is, okay? So just explain what you do. Okay? So in your situation, what you do? What is this? Okay, because A just means that I choose something among something. What you do concretely there?
I choose one from the half.
Why the half? By color, be careful. Color is not black and red. Okay? When I say the same color, it means that both spade, both club, both diamond, or both earth. Be careful. Okay? So that's why be careful with the 26. 26 is the number of black and the number of red. Nothing to do with the notion of color. I use index. Okay? Be careful. And I say that here, okay, when I explain, okay, both have the same color, I see the 4 possible cases, and then I do the complementary set, something that is very clear. I say that it's not the only way to do, maybe, okay, if you want to do it directly, that is, describe perfectly what is the meaning of the 2 cards don't have the same color, it's possible to do, but be careful in the description, okay, of this set. I don't want to describe it, that's why I use the complementary set. Okay? And because I have done this previously. I think about the complementary set because I have done this job before. That is in relation with the computation of both have the same color. Okay? Okay. Question C. What Find the probability that the first is a spade and the second is an earth. So I write this one, okay, here, now. So the first is a spade and the second is an earth. But the only thing I have to take into account here is the fact that I can't be a spade and an earth at the same time. Okay? So, first, what? Spade. Second, earth. Okay. Once again, over 22 by 21. Okay. So how many possibilities that the first is a spade and the second is an earth? Well, for the first, I have 13 possibilities. And for the second, I have also 13 possibilities because, okay, heart and spades are disjoint sets, okay? It's not possible for me to be both spade and heart, okay? So I have 13 because it's the number of spades related to the first drawing. And for the second one, okay, I have also 13 possibilities because, okay, in my deck it remains 13 hearts. Okay? 13 this way. And the argument is that it's not possible to be both spade and heart. Okay? And finally, the probability of one spade and one earth. Not the same. What is the set one spade, one heart? Okay, keep in mind that I take into account the order. It means two possible disjoint cases. The first is a spade, the second is an heart, or the two being disjoint, the first is an heart and the second is a spade. Okay? So it's not exactly the previous answer, but it is 2 times the previous answer. Okay? Because here I consider just the first spade and second heart. I have to take also into account, okay, the first heart and the second spade. Okay? So it's 2 times what I have previously computed. So be careful in the way to explain for an exam. Okay? Of course, when I correct an exercise, I can speak. So I write things, okay, but I do also explanation, okay, using words. During an exam, you don't have the possibility to do, okay? So, in the paper, I want some explanation. If you just write this kind of thing, okay, without any type of explanation, it won't be that good, okay? So here we speak about basic things, okay, but you have to be precise in the explanation. They need to be present, okay, short if possible, okay. It will help me to correct in a quick way, okay, that you need. So typically you see that here it's a short, let's say, correction of the exercise because I spoke, okay, a lot, maybe. Okay, so finish with the exercise for today, for the summer list. Okay, I will continue next session. And so I just check that it works, yeah. And let's use the slide. So in my website, okay, it's what I called here, let's see. You have the prerequisite. Proba 3, okay, is in fact the first after the prerequisite that is here. Proba 1 and Proba 2, okay? So let's as you will see here, from the probability part, okay, so you will have number in the definitions here. You will have number in proposition. So here it starts by definition 7 and proposition 4 because you have the prerequisites, okay, with definitions inside and propositions, okay. And typically, you have also in my website some proofs in the course that I won't do with you on the board, typically because I have a small board. So you have here proof of the course 1, proof of the course 2, and I will use the same numbers. Okay, so you will see in the proof of proposition of the course 1, you have, for example, the proof of proposition 5, if I remind you, that okay, is a reference to the slides. Okay, so a priori everything is coherent here. Okay. So probability and independence, it will be mainly two definitions. The two definitions that are a little bit, for the definition of a probability, something that is more theoretical than what we have seen previously. So in what I have said just before the break, okay, I have said to you that, okay, in real life, okay, we have intuitive ways to introduce probabilities, okay, and more or less, you have to compute the number of elements, okay, in a set. So it's typically what we have done in exercises 28 and 29, okay, to count, okay. But for a more complex situation, and typically, okay, for what you are going to do in the second semester, that is to try to model, okay, some economic or financial situations, okay, typically you need to have more flexibility in the definitions, okay. So from now on, okay, what I will call a probability will be something that is given by this definition here. I will comment it just after. But we have to keep in mind that this definition here is just an extension of what we have seen before the break. Okay? So don't think that this definition is something that is completely, okay, different from what we have done before. It is just an extension to take into account more situations and to be able to compute the probability of more sets, okay, in more complex situations. Because typically, if I come back to the dice, in my situation with the dice, okay, I have 6 outcomes. It means that I have just a finite number of possible outcomes. But imagine that you are in the situation where you have an infinite number of outcomes. It means that for some sets, it's not possible to compute the number of elements because it is infinite. So you can't use the formula, okay? P of A equal to N of A over N of omega, because in general, okay, in real life problem, okay, omega will be infinite. That's why I need to drop this definition and to extend it to have this, okay? So, omega will be, as in the case of the dice, okay, my universe. Okay, so a probability is always related to the universe. So, and what is a probability? A probability is a mapping. A probability is a mapping that associates to a set a number between 0 and 1. Okay? So a probability is a mapping defined on a set A and with values in the interval 0, 1. Meaning that to a set A, I associate P of A, that is a number belonging to 0, 1. Okay? And what is A? A is something that is included in the power set of omega. And what is the meaning of this one? Simply that A is a set of subsets. You have here a set that contain as elements subset of omega. And to each of these subsets, you are able to associate a probability. I remind you the definition here, the power set of omega. It's a definition that is reminded in the prerequisite, the power set. It is just the set of all the subsets of omega, the set of all the subsets. And this one is a subpart of the set of all the subsets, so it's a set containing some subset of omega. Okay? So a probability is a mapping associating to some set a number between 0 and 1, so that is something that is positive, okay, greater than 0, and less than 1. And it has to fulfill, okay, two statements, and only two. The first one, so omega universe, okay, a probability will be a mapping from A into 0, 1, okay? So I'm not sure that it is necessary to copy the definition because you have the slides, huh? Mine is without mistakes, okay, so maybe it's better to listen to me, okay, and to maybe to write the remarks we are going to see together. Okay, here for the moment I just copy this one, just saying that here it's the power set and that A is a set of subsets. Okay, is this one that is important. So I suppose two things. First, that P of omega is equal to 1. Because I want to have what we call a probability, something with the probability of the universe, or P of the universe is 1. Okay. And a second property, that seems to be a little bit more strange here, that is what we call the sigma additivity. What is the sigma additivity using words, okay? I said that for P to be a probability, I want the following property to be fulfilled. That is, if I consider a sequence of pairwise disjoint sets, then the probability of the union is equal to the sum of the probability. So, for all sequences of sets, okay, of pairwise disjoint sets, the probability of the union, and I have already defined what is this one in the beginning of the session, the probability of the countable union is equal to the infinite sum of all the probabilities. The only thing I have to precise in this second statement is what is the meaning of pairwise disjoint. Pairwise disjoint means that they are disjoint if I take them 2 by 2. Pairwise disjoint means in fact this one. AN intersected with AP is equal to the empty set if N is different from P. So for example, A0 intersected with A1 is empty set. A1 intersected with A2 is empty set. A0 intersected with A2 is empty set. Okay? No overlap between these sets. Okay? And in these situations, the probability of the union is equal to the sum of the probabilities. Okay? So, if we compare this definition with what I have done with the dice, okay, we see that with my example with the dice, okay, I have a natural way to define the probability, counting number of elements, and here it seems to be a little bit more theoretical. Okay? But let's see what happens with these definitions, and in particular with these natural consequences. Okay? I say the following. If I keep this definition, probability, I have directly this one. This proposition 4. Something that is here, okay, more comfortable. I said that, okay, I have this definition that seems to be a little bit theoretical, but I have all the way to compute the probability as I have done previously in the case of a dice. Typically, the probability of the empty set is 0. The probability of the complementary set is 1 minus the probability of A. The probability of the union is equal to P of A plus P of B minus P of the intersection, okay, and so on. And this proposition is just a consequence of these two statements, not more, okay? So maybe let's see what happened for the proof of this proposition, okay? So it means that I have my two statements here, okay? My two statements, and we are going to see what happened in this case here, okay? To prove the proposition. So what I will do, I will erase. So for the moment, I come back to the definition. So I erase my board because you have the definition on the slides of what is the probability. And we are going to prove some statement of the previous proposition. Okay, so proof of proposition 4. The next one, okay? In the slide number 3. So the first thing I have to prove is that P of the empty set is equal to 0. In the case of the dice, no problem, because it's the number of elements in the empty set over the number of elements in omega. But here it's no more this definition. The definition is the one of the slides, okay? What is more, for the moment, I don't have the fact that the probability of the complementary set is equal to 1 minus the probability of A. So I can't deduce for the moment this one from the fact that the probability of omega is equal to 1. Okay? So I have really proved it, okay, only using my definition, without anticipating, okay, things that will be a consequence of this definition. The way to do, well, is to use the statement 2 in this definition. Okay? Using the second point of the definition and taking for the sequence AN a sequence with sets that are, okay, all of them are the empty set. I have the right to do because as a sequence, okay, I can choose any sequence with the only condition that I have a sequence of pairwise division sets. And what is the meaning of being pairwise divisions? If I take the intersection 2 by 2, I obtain the empty set. And of course, in the case where all the elements of my sequence are the empty set, if I take two elements, I do the intersection empty. Okay? So if I use 2 and this sequence, this very particular sequence I have the right to choose, I can use the property in red in the slides. That is, the probability of the union of all of them is equal to the sum of the probabilities, because AN is a sequence of pairwise division sets. What I obtain from this one? What is the union of AN if all the AN are empty? I have here P of the empty set simply, because the union of all the AN, if all the AN are the empty set, is just the empty set. I have nothing inside. And so I have P of the empty set that is equal to what? At the sum of terms that are just P of the empty set. And what is the consequence of this one? But if I want this equality to be true, okay, in fact I have only, a priori, I may have two possibilities. P of empty set is 0 work. It's not the only one, because if I have P of empty set is equal to infinity, it can also work. But here, I know that the probability is a mapping into 0, 1. So it's a number between 0 and 1. Since it is a number between 0 and 1, necessarily, from this equality here, P of the empty set is equal to 0. Okay? Because of this relation here, and because of the fact here I have a number between 0 and 1. Okay, so this number equal to this sum if and only if all the terms are equal to 0. Okay? So P empty set equal to 0 is just a consequence of my second statement. I use nothing except the second statement in this definition. Okay? Simple. And from now on, okay, when I will have a probability in this sense, I know that P of the empty set is equal to 0. Okay? Second point here in the proposition. Well, the small a here. If A intersected with B is equal to empty set. So my hypothesis is that, okay, A intersected with B is equal to empty, and I want to prove that P of A union B is equal to P of A plus P of B. Why not? Okay? And once again, it's not, as in the case of the dice, a consequence of my definition, but I want to prove that it is a consequence of my theoretical definition here. Okay? So once again, it will be a consequence of the statement 2. And what we are going to take, so using 2, the statement 2 in the definition 7, and taking, for example, for A0, I take A, for A1, I take B, and then for an, I take the empty set for n strictly greater than 1. So you have here a sequence of sets that is pairwise disjoint, in the sense that they are disjoint 2 by 2, because A and B are disjoint, in fact. So I have a sequence of pairwise disjoint set. So I can use the definition, that is the probability of the union is equal to the sum of the probabilities by the definition 7. But what I have here, I have just the first one, that is A, the second one that is B, and all the other are empty. So here I have simply the probability of A union B. And here what I have, by P of A0 is equal to P of A, P of A1 is equal to P of B, and all the other are 0. So I have simply P of A plus P of B. And it's exactly the second statement of the proposition 4. Okay? Question? So it's important, I just want to make emphasize on the fact that proposition 4 is a consequence of definition 7. Okay? It's not the definition of the probability, proposition 4, it's a consequence of my previous definition. Okay? Are you okay with what I have done? So I have proved that P of A union B is equal to P of A plus P of B in the case where they are disjoint. Now I want to prove that the classical formula that P of A complementary is equal to 1 minus P of A. I say that it is just a consequence of the previous. the previous statement, the statement P in the proposition, okay, tell me that the probability of the union is equal to the sum of the probabilities if I have two disjoint sets. Okay? But here I have two disjoint sets. I can take for A, and for B, I take A complementary. I have here two disjoint sets. They are disjoints. And using small b, I have what? That P of A plus P of A complementary is equal to P of the union. What is the union between A and A complementary? The universe. And I know from the definition 7 that P of omega is equal to 1. P of A plus P of A complementary is equal to 1. It's exactly the statement I want to prove, the small c. Okay? It's exactly this one. Are you okay? Once again, okay, I use only things that I have already proved. And nothing that I suppose to be true. Okay? I start from the definition 7 and prove step by step all these things. Now I want to prove the classical formula. P of A union B is equal to P of A plus P of B minus P of the intersection. Okay, and I want to prove it using the definition 7 or the things that I have already proved before. Okay? Allez, let's do a little picture, okay, that is not a proof, but just to have in mind what happened. I have A and B here, okay? And in fact, it is possible for me to decompose A union B. So what is A union B? Okay, it is both of them, okay? This one here. I have only one color, so this is A union B. And I can see that A union B may be decomposed in three parts. This one, and this one. What is the meaning of this one? I am in A, not in B. I am in both. I am in B, not in A. Okay? I can write the following using notations of prerequisites. A union B. So to be in the union, that is to belong to at least one, means that I am in A, not in B, or in A intersected with B, or in B minus A. That is in B, not in A. So definition introduced in the prerequisites. This one means that I am in A, not in B. It's what we call A minus B in the terms of sets. A in A, not in B. Here the intersection. Here I am in B, not in A. And this symbol means that it is a disjoint union, in the sense that I see that I have three parts without overlaps. Okay? Intersections being empty. Okay? So I have this one. I have written A union B using three disjoint sets. But I have proposition 4, small b, that tell me that if I have a finite number of disjoint sets, okay, I know what to do. Okay? So from small b, P of A union B is equal to what? P of A minus B, P of B minus A, plus P of A intersected with B. And if I want to continue, okay, I have to express this one. Okay? I am interested in what is P of A minus B. and what is P of B minus B. So what is A minus B? So in order to find what is the probability of A minus B, just remind that A is equal to A minus B, disjoint union with A intersected with B. So what is the meaning of this one? It means that if you consider A here, A, and this here, I can write A as this part, that is A minus B. I am in A, not in B. And this part, that is the intersection. And with these two parts, you have everybody. Okay? These two being disjoint, okay, I have that P of A is equal to P of A minus B plus P of A intersected with B. Okay? And in fact, I obtain from this an expression for both of them here, that is what? P of A minus B is equal to P of A minus P of the intersection, and here, by symmetry, P of B minus P of the intersection. If you replace this one and this one in this expression, you obtain exactly the small d. So P of A minus B equal to P of A minus P of the intersection, you plug it here, you plug this one also here, and you obtain exactly that this one is equal to P of A plus P of B minus P of the intersection. I have minus P of the intersection because here I have plus P of the intersection, but I subtract it twice. Okay? I have this one. So the classical formula that it would be possible to use even if I have a theoretical definition of my probability. Okay? I have this. And the little last intuitive result. Okay. So are you okay with this proof? Once again, I use only things I have proved. Okay, I suppose nothing, and there is nothing to do with counting elements in a set. Nothing to do. Okay. So small e, a thing that is intuitive, that is, if you have A that is a subset of B, the probability of A is less than the probability of B. If you have a smaller subset, its probability with B will be smaller. Okay? So I want to prove that A included in B implies P of A less P of B. Why I have this? I can use, in fact, this little picture here to remark once again that I have this, that A is equal to A minus B disjunct union with the intersection. Okay? If I write this, I can write this, but it's not that interesting, okay? Because in the case where A is included in B, here I have empty set and here I have A. So I have the right to write this, but it's not what interests me. I can write, but it's more B equal to B minus A union B intersected with A. If I write this, okay, so in the picture, okay, I say that B is equal to B minus A, that is D parts, union what I have, okay, in common, that is the intersection. If I suppose that A is included in B, what is the intersection between both of them? A, simply. So in this case, this is equal to A because it's not true in general, because A is included in B. Okay? And so I have B that is equal to B minus A disjoint union with A. If I use the small b of my proposition I have already proved, okay? I can say what? That P of B is equal to P of B minus A plus P of A. And what can I say about this number? This number is a probability, so it is a positive number. And so, if I can write P of A, a positive number plus P of A, it means that P of A is less than P of A. Okay. Once again, I can deduce this simple thing, okay, from the fact that I have my definition set. Okay? So I have this. So at this stage, I have a theoretical definition, but I see that in practice, the way to compute probabilities will be the same as in the case of the dice. Exactly, because I have the same kind of propositions or the same kinds rules of computation for P. Okay? Questions in the proofs? Okay? So, why, if I have the same rules of computations, why I have to pass from the definition with the dice to the definition 7, okay, if I want to deal with more complex examples of probabilities computations, okay? Typically because with my definition 7, I have this kind of result. Okay? If I come back to the case of dice, the only probability that I am able to compute are the probability of sets that I am able to describe explicitly. Okay, so I am in a finite situation, okay? If I compute, for example, the probability to be odd for the outcome, okay, I have to compute the probability of 1 plus the probability of 3 plus the probability of 5, okay, and so on. And in any kind of situation, the probability of a set will be a consequence of my ability to describe it explicitly. To have a list of the elements that interest me. Okay? If you are not in a finite set, in general, it's not possible to do such a list, okay? And you may want to compute the probability of sets that are not that easy to define. Typically, okay, sets that may be seen as the limits of other sets in some sense, okay? So it's typically the point of this theorem that is called theorem 4 that tells me the following. So if we suppose that I am a probability, that is, I fulfill this definition, okay, then I have the following consequence that is a really very important consequence in fact, okay? So maybe in this course, okay, you won't see in all the details why it is that important, okay, but believe in me that it is really, okay, a very important consequence of the definition 7 that is not possible if we keep a definition of the type of the dice. Okay? So what is this consequence? It means that when you have a sequence of set that is increasing or decreasing, okay, you are able to say something about the limit of the probabilities. Okay? So typically two statements. And for the proof of the theorem, okay, it is in the list 1 of the proof of the course. Okay, I won't do the proof because it's not that technical, but I have a small board, okay, and I didn't want to make too much confusion at the beginning. But it tells me that if I have an increasing sequence of sets, increasing means that A0, A1, A2, A3, and so on. Okay, I have sets that are bigger and bigger in the sense of inclusion. Okay, when I speak about sex, when I mean sets, increasing means in the sense of inclusion. Okay. If I have an increasing sequence of sets, the limit of the probabilities exists and is equal to the probability of the union of all of them. Conversely, if I have a decreasing sequence of sets, meaning that I have A0, A1, A2, A3, and so on, okay, so decreasing in the sense of inclusion, then the limit of the probability is equal to the probability of the intersection. Okay? So you have two dual statements in some sense. Here, the union represents the biggest of all of them because I have an increasing sequence. Okay? Here, the intersection represents the smallest of all of them because I have a decreasing sequence. And in both situations, okay, the limit of the probability is equal, in one case, to the probability of the union, in the other case to the probability of the intersection. Okay? And typically, okay, you will see, not typically in this course, but maybe in the second semester more or in next year, okay, if you follow some courses of mathematical finance, okay, that sometimes, okay, I want to compute the probability of such objects here and here with the AI that is increasing or decreasing or increasing, and if I want to compute the probability of this union or the probability of this intersection, even if the union may be very, very complicated and the intersection very, very complicated, it is sufficient for me to compute the limit of the probabilities. So I just have to compute a limit in order to compute the probability of someone that can be very, very strange. If you have a sequence of sets, if you take the union or the intersection, what you may obtain may be really, really strange. Okay, and here in this situation, thanks to the definition 7, okay, I have a way to compute these probabilities. Okay. So I have this, and it is a consequence of what we call the sigma additivities. The fact that if I have a sequence of pairwise division set, the probability of the union is equal to the sum of the probabilities. If I have this, I have also these two things. Okay? Try to do this exercise at home for the next session. I will correct it next session. It's a little exercise. Okay? And I give you an hint in order to do it. To do the question 1, do an induction as defined in the prerequisites. Okay? So you have to prove something for any n. You have to prove it for n equal to 0. Suppose it for n, prove it for n plus 1. You have the result by induction. Okay? So it will be the way for you to remind what is an induction. And then you see that what is the difference between this one and this one? I have just to pass to the limit here. And in order to pass to the limit, I want you to use this one. Okay? And this result, this little exercise is interesting by itself because we know from the definition 7 that the probability of the union is equal to the sum of the probabilities if I have a sequence of pairwise division sets. And the meaning of this exercise tells me that the probability of the union is always less than the sum of the probabilities. And here I have no hypothesis concerning the fact that I have a sequence of pairwise division set or not. Okay? It's true in great generality. So really try to do it at home, okay, and I will correct it next session. And it's, repeat, for the 1 induction, for the 2 use theorem 4 small a. Okay? I will finish this session with a little definition concerning independence. What is the meaning of independence between sets? So we do the definition for 2 sets and then for a finite number of sets. Okay? Be careful because it's not that evident the way to pass from 2 to 3, for example. Okay? So let's start with definition 7. okay, A and B are independent, okay, if the probability of the intersection is equal to the product of the probabilities. Okay, so I will introduce one notation here. A and B independent will be denoted by A, this symbol here, the symbol of orthogonality. Okay, it's a notation to write are independent. Maybe I will use it, okay, sometimes. Okay, it's just a notation concerning independence. But what is the meaning of this? It means that the probability of the intersection is equal to the product of the probabilities. Definition of independence. Okay? For two sets. So if I ask you to prove that two sets are independent, you have to compute the probability of the intersection and prove that this is equal to the product of the probabilities. Okay? What happens if I have more than two sets? Okay? But the definition is the following one. So it's the definition B, okay, in the slide 5 here, okay? So we say that A1, A2, AN are independent. So I have something that seems to be complicated here. What is the meaning of this one? It means that I have n sets, okay? I consider all the possible subfamilies with more than two elements, okay, with these n sets. So I will consider, okay, the pair, the triple, the quadruple, and so on, okay? The n of them. And I want that if I consider all the pair, that the probability of the intersection is equal to the product of the probability. If I consider all the triple, the probability of the intersection is equal to the product of the probability, and so on. So typically, to give you an example, for n equal to 3, if I want you to prove that A1, A2, and A3 are independent. Okay? In fact, I have to prove that I have the probability of the intersection that is equal to the product of the probability for each subfamily, okay, with more than two elements. So what is the meaning concretely of this one? Now I have to consider all the pairs. What are all the pairs? I have A1 intersected with A2, I have A2 intersected with A3, and I have A1 intersected with A3. Okay, all the three pairs I can build from this one. Okay, and I have a single triple, that is A1 intersected with A2 intersected with A3. Okay? If you come back to the definition B here, my meaning is that I take for k equal to 2, and I obtain these ones, all the pair. Well, for k equal to 1, in fact, it's true, but it's meaningless, the condition. And for k equal to 3, okay, I have the triples. And I have to check that, so to prove that A1, A2, A3 are independent, you have to check that this one is equal to this product. Also for this one. Also for this one. And in particular, you see with this little example that to be independent for three sets doesn't mean that they are pairwise independent. They are not only, they are independent 2 by 2 if we have three independent sets, but we have more than this. Here you have the independent 2 by 2, and you have an extra condition that is the probability of the whole intersection is equal to the product of the probability. Okay, so I repeat that. even in the case of three sets, to be independent or to be independent 2 by 2 doesn't mean the same thing. The notion of being independent is stronger. It implies that they are independent 2 by 2, but it is stronger. Independence 2 by 2 doesn't imply that we have the independence. Okay? I can write it here. Independence doesn't, is not equivalence, this way is not equivalent to pairwise independence for n vector equal to true. So you can be independent 2 by 2, but not being independent in the sense of this definition. Okay, so I repeat that if you have, for example, 4 sets, if I want you to prove that they are independent, you have to prove that for all the pairs, the probability of the intersection is equal to the product of the probability. That for all the possible triple, the probability of the intersection is equal to the product of the probability. And that for the word intersection, the probability of the 4 sets, the probability of the intersection is equal to the product of all of them. Okay? And we will see an example of this, okay? I write it here, I will do it next week, next session. Have a look on the exercise 5 of the list 3, what I have called a TD3, okay, in my page, okay, tutorial number 3. The exercise 5 of the list 3 of exercise. So the list 3, if you come back to my web page, okay, in fact, you have here the prerequisite, the course of probability, and you have here TD3, TD4, TD5, and so on, okay? If you take the exercise 3 and 5 of this list here, it's something that is in relation with this one. To show you an example where you have pairwise independence, but where the sets are not independent because it doesn't fulfill the last condition here. It's a basic. So you can have a look at home for next session if you want, okay? I have this one. Or maybe I will conclude by this for today, okay? So have a look. Mainly, okay, so I have defined few things today. We have done basic exercise, but I want you to take time at the beginning, okay, to spend time on the prerequisite if you don't have done the job during the holidays. It's really important for the beginning, okay, because you have a lot of notations, as you can see. Okay? So see you on Thursday, okay?